If you've ever seen a really high-end display, maybe a huge 4K movie screen, or one of those concept car dashboards that just looks impossibly crisp, you know that the real difference between a good image and a truly breathtaking one, it all comes down to color fidelity. We're talking about the holy grail of light here, absolute purity. Think of the, I don't know, the intense, hypersaturated greens of Wakanda in the movies, or maybe the perfect glowing red of a control panel on the Starship Enterprise.
Right, and that kind of purity isn't just about making a color bright. It's about light that is perfectly targeted
Yeah.
and stable. And, for a long time, researchers have known exactly which materials can deliver that kind of precision. Lanthanide nanocrystals.
These materials are, they're basically chemical wonders. They offer what the research calls narrow band emission.
Which in plain English just means the light they produce is incredibly pure. The spectrum is super tight, less than 10 nanometers of spectral width.
And they're tough. They have exceptional photochemical and thermal stability. They last, and they glow with a perfect specific color.
They are, and this isn't an exaggeration, the perfect color emitters for the next generation of, well, everything. Screens, lighting, sensors. But, and this is a huge but, they come with this massive deal-breaking challenge that's kept them out of commercial tech.
And what's that?
They're electrically insulating.
Ah, so it's like having the world's most powerful engine, but there's no way to get fuel into it.
Exactly. You've got this perfect power source, but it's wrapped in, I don't know, a thick layer of rubber.
The base materials, like AlMF4, they're great chemically, but you can't get an electrical current through them.
Right, they're insulators. And in an LED, an electroluminescence device, you have to pump electrical current directly into the material to make it glow, because these lanthanide crystals resist that current direct injection. It's just incredibly inefficient.
So you can make them glow with another light source, but you can't just plug them in.
You've got it. And if you can't do that efficiently, they're basically useless for mass market displays. It's been the main barrier for decades.
So how do you solve a problem that seems, well, fundamental to the material itself? That is the question that's been answered by the monumental research we're diving into today. Our deep dive is based on a paper published in Nature by Jingtan Peng Zhang and their colleagues from places like Heilongjiang University and the National University of Singapore. Their team engineered a molecular solution that acts like a missing wire, an electrical bridge that turns these insulating crystals into super efficient LEDs.
Yeah, let's unpack this because it's just a beautiful example of using clever molecular engineering to sidestep a huge physics problem.
Okay, let's do it. So the core breakthrough here is taking these tiny little nanocrystals, we're talking 4 nanometers in size, and coating them with these very specialized organic molecules called ligands.
Now, a ligand is just a molecule that sticks to the surface of the crystal, but these are on another level. They're a specific type called functionalized 2-diphenylphosphoryl benzoic acids, or RPPOA.
That's a mouthful.
It is, yeah. The specific one they focus on is called CZPEPO.
Okay, so that dense chemical name, what does it actually do? The concept here is brilliant, right?
It is. It forms what the researchers call a soft electronic interface.
A soft electronic interface. You could almost think of it like a molecular grappling hook, or an energy bridge that latches onto that insulating surface.
That's a perfect analogy. And that hook is so critical because it does 2 essential jobs at the exact same time. Job 1, it acts as the charge transport media. It's the wire. It's what gathers the electrical energy from the device's circuit.
Okay, so it collects the energy. And job 2?
Job 2 is that it's an excitant harvester. Once that electrical energy is gathered, the ligand funnels it like a packet directly into the lanthanide core.
So it completely decouples the charge transport from the light emission? The crystal itself doesn't need to be conductive anymore.
Exactly. The insulating core is still insulating. The CZPPOA coating just handles all the electrical traffic and makes the final delivery.
That's the key insight. They didn't change the crystal, they just built a molecular bypass around the problem.
And the architecture of the ligand is what makes it possible. It's a donor-acceptor hybrid.
Meaning one part gives electrons and the other part takes them?
Precisely. The design creates this perfect electronic gradient, and by tweaking the molecules, they could tune how energy moves within that bridge.
So they could perfectly match the energy they harvested to what the lanthanide ion needed to glow.
You got it.
And what's really fascinating to me is that this didn't just solve the electrical problem, it also fixed a practical, like a manufacturing problem.
Yes. That's a sign of really comprehensive design. The CZPPOA coating dramatically improved the physical quality of the film.
Smoother films, you mean?
Much smoother. They measured the surface roughness, and it dropped from 1.24 nanometers for the uncoated crystals all the way down to 0.71 nanometers.
Okay, why should we care about a drop in roughness of half a nanometer? What does that mean in the real world?
Well, think about making a screen. Smoother films mean fewer defects. It means better integration into the complex layers of a device, which means higher reliability, longer lifespan. If your molecular bridge is also making your material easier and better to build with, you have something that's ready for the factory, not just the lab.
That's a powerful link between the quantum and the practical. So let's move from that molecular bridge to the quantum engine that makes this energy transfer so ridiculously efficient.
Okay, so this is where it gets really interesting. Lanthanides are picky. They need a very specific kind of energy state to glow brightly.
A triplet state excitant, right?
That's the one. When the ligand captures the electrical energy, it usually starts in a different state, a singlet state. If the energy stays there, it just kind of fizzles out as heat, useless. The ligand has to convert that singlet energy into a triplet state before it can hand it off to the lanthanide.
And that conversion intersystem crossing, or ISC, is normally a pretty slow, difficult process.
It is. But here's the magic. They found that just by being attached to the lanthanide ion, the whole process speeds up dramatically.
How does that work?
It's something called the heavy atom effect. The lanthanide ion is a heavy atom, and it creates these intense little magnetic fields that basically nudge the electrons in the ligand. It kind of forces them to flip their spin from the singlet state to the triplet state. The lanthanide itself is the catalyst.
Wow. So the thing that needs the energy is also the thing that helps prepare the energy for delivery.
Yes, and speed is phenomenal. The whole process happens in under a nanosecond, 1/1000th of a second.
And that speed is what preserves the energy and stops it from being wasted as heat.
Right, and that leads directly to the final step, triplet energy transfer, or TET. This is the moment the ligand passes that perfectly prepared triplet energy right into the heart of the lanthanide, and poof, you get light.
And the efficiency numbers here are the real
Wow
moment in this paper.
Oh, they're staggering. The researchers reported an ISE conversion efficiency, that singlet to triplet flip, of an unbelievable 98.6%.
Almost perfect. What about the final handoff?
The triplet energy transfer was also near perfect. They clocked it at 96.7% for the best films.
Just think about that. You start with an insulator that blocks electricity, and with this one molecular trick, you end up with a system where almost every single packet of electrical energy you capture gets successfully turned into pure, perfect light.
It just completely overcomes that activation barrier that has held back lanthanide research for so long. It simplifies everything.
And they didn't just prove it in theory, right? They actually built working LEDs.
They did. They built full 4-layer LED devices with these new nanocrystals in the emissive layer.
So how did they do? What were the industry metrics like?
Very, very competitive. The external quantum efficiency, or EQE, which is a key metric, topped 5.9% for the green-emitting devices.
Okay, 5.9%. How good is that for this kind of material?
It's a massive leap. I mean, for this specific class of material, that number is a 76-fold enhancement compared to what they could get without the special ligand coating.
76 times better.
76 times. It's like taking a dim little light and making it 76 times brighter with the same amount of power. It's a huge jump.
And what about power consumption and stability? That's what really matters for, say, a phone screen.
Both look great. They hit a power efficiency of 7.66 lumens per watt. That's getting into the range of early commercial OLED devices. It suggests really good potential for battery life.
And the turn-on voltage was low, only 4.1 volts, which is totally standard.
And, maybe most importantly, reliability. The CZPAOA devices were way more stable over time than control devices that used other next-gen materials, like perovskites.
Perovskites are known for being amazing but fragile, right?
Exactly. Lanthanides give you both the perfect color and the toughness.
So let's get back to that promise of perfect color, because this system seems to unlock it in a whole new way.
It really creates this unprecedented tunability. By just changing the chemical recipe a little bit, mixing the green-emitting terbium with the red-emitting europium, they could get a seamless transition of colors.
So you don't need to rebuild the whole LED to get a different color. You just change the powder you put in.
Precisely. That simplicity let them create everything from pure green to yellow, orange, and even high-purity white light.
And we're talking about a really true, clean white light.
Yes, hitting industry-standard color coordinates that match important illuminants. It's the kind of pure white you need for professional displays.
And it goes beyond what we can see, too. They also got it to work in the near-infrared spectrum.
They did. By doping with neodymium ions, they got a sharp emission at 1064 nanometers.
And why is near-infrared so important?
Well, that's critical for things that aren't displays. Think about it, advanced medical diagnostics, night vision tech, or even emitters for cutting-edge neuromorphic computing. This isn't just about a better TV screen. This is about enabling a whole suite of future high-tech applications that need stable, specific wavelengths of light.
Okay, let's take a breath and recap the three biggest takeaways from this deep dive into the work by Jing Tan, Xiaogang Liu, and their teams.
Takeaway number 1, the insulator glows. They finally cracked the code on making electrically insulating lanthanide nanocrystals work in LEDs, all by using that engineered CZ-PPOA molecular ligand. The decades-old delivery problem is solved.
Right. Takeaway 2, the molecular powerhouse. These ligands act as perfect little energy bridges. They achieve stunning near-unity efficiency, up to 96.7%, by capturing electrical energy and channeling it right where it needs to go.
And takeaway 3, a universal color platform. This breakthrough lets you precisely tune the color output across a huge gamut, from pure greens to high-purity whites and even into the near-infrared, just by tweaking the chemistry, not the complex device architecture.
So this work really provides a modular, super-efficient strategy for controlling energy in a whole class of nanomaterials that were pretty much unusable before.
It does, but we should mention the one remaining challenge, which the authors themselves point out. Even with all this efficiency getting energy in, the overall brightness is still limited by how fast the lanthanide atoms can get the light out.
The radiative lifetime, right. The atoms emit pure light, but they take their time doing it.
Exactly. They don't turn off fast enough to produce the absolute highest flux of photons possible.
So if they just solved the molecular challenge of getting energy in, the next frontier is solving the atomic speed limit of getting light out.
That's it. And that brings up a really big question for you, our listener, to think about. If future research can overcome that intrinsic speed limit of the light emission itself, how quickly could these incredibly stable, color-pure lanthanide displays replace our current screen technologies? And what kinds of revolutionary applications would that combination of rugged stability and high efficiency unlock? Maybe in transparent displays, or wearable tech, or even in sensitive quantum systems. The molecular foundation has now been laid.